Alright, welcome back. In this, we're going to go over hydrohalogenation of alkynes. I made a lifetime total of $521.34. We got an easy one for you guys today. Here's what we're going to do, the overview. First, I'm going to talk about what hydrohalogenation is of alkynes. Then we're going to go over the recipe and the first mechanism. There's actually two mechanisms, two proposed mechanisms. They're pretty easy, don't worry about it. So this is the second one, and then we're going to go over 4 practice problems. So, not too bad. In other news, I got my first hate comment, so I'm actually very happy. I'm actually famous. And the comment actually made me laugh a bit. The comment said that I am extremely childish when I teach. And I'm like, fuck yeah, I am. I am childish because you gotta think about it. I would fall asleep teaching this kind of stuff if I wasn't childish. I mean, like, organic chemistry is pretty boring if you're just sitting on, I'm just sitting on my laptop, on my iPad teaching it and doing this for hours. I would fall asleep. So I gotta add some humor. So it does not mean that you guys are gonna like it. I mean, I like it, but you guys may not. But seeing from the statistics, I know you guys are liking it, or majority of you are, because a fun fact, my like to dislike ratio is exactly at 99%. So it is one of the highest recorded on YouTube, as far as I know. So yeah, thank you. Now that does not. Now I don't have a gun to your head saying you have to watch my videos. No one has that, right? You're not in handcuffs or anything. You can go watch Organic Chemistry 2 or Khan Academy or Chad's Prep if you wanted to. No one's forcing you to be here. But if you do want to be here, you're more. Thank you. Go get some popcorn and grab some beer. We're gonna have some fun. Okay. Hydrohalogenation of alkynes. Okay. Hydrohalogenation of alkynes is the addition of one hydrogen and one halogen, or the addition of 2 halogens and 2 hydrogens. I will explain. But first, the halogens are installed on the more substituted carbon. Okay, here's the first possibility. We have our alkyne. We add HX. X could be bromine, chlorine, or iodine. Does not matter. It just cannot be fluorine. We add the halogen on the more substituted carbon, and then the hydrogen goes on the less substituted carbon, which we do not draw in. The other version is using excess HX, and I'll explain why a little bit later, why this works. What this does is we have our alkyne, but when putting excess of a hydrogen and a halogen, we install 2 halogens and 2 hydrogens, but we get an alkane. We do not end as an alkene like this one. I'll explain why. But first, the recipe. Okay, we need an alkyne. I think it's pretty self-explanatory, and we need our HX, hydrogen and bromine, chlorine, or iodine. Never fluorine. Here's the mechanism. This is exactly like hydrohalogenation of alkenes. This is just with an alkyne. The pi bond is going to attack the hydrogen of our reagent. It's going to kick the halogen out. The hydrogen is going to bind to the less substituted carbon. The reason this happens is because we get a carbocation formation. This is going to happen no matter what. The thing is that we have to make sure that carbocation is as stable as it can be. And the way it is stable is when it goes to the more substituted carbon, because carbocations love more substituted carbons. This side is more substituted than this side, so that is why the carbocation goes there, and the hydrogen must go there. Well, we have now an electrophile, so our nucleophile, our lone halogen, is going to attack our electrophile, and it's going to bond to the more substituted carbon. Now, here's the thing. Stability is in question. This carbon actually has a lot of power. It's very high in energy. And when something is high in energy, it's less stable. And you're probably wondering, wait. Less stable? I thought this should be more stable because we just added to the more substituted carbon. You would be right normally. But chemists realized doing this reaction in real life, this does not really happen all the time. Sometimes it happens, this reaction happens, sometimes it does not happen. Sometimes they witness that the carbocation actually never forms. Well, if it never forms, then there must be another mechanism. And there indeed is. We call this a termomolecular process. In other words, a threesome. This is literally what's happening. 3 molecules are involved all at once. Let me explain. One equivalent is going to bond to this carbon right there. The pi bond is going to attack the hydrogen of the second equivalent. So it's going to do the exact same thing as basically this mechanism right here. Now, briefly, when this happens, it creates this transition state where this is bonded and this is bonded. This one's bonded to this carbon and this one's bonded to this carbon. One will be bonded to more substituted carbon and the one that will be bonded to less substituted carbon. Now, here's the key point. We create a partial positive charge when we do this. That means the halogen is going to be attracted to the side that has the partial positive charge, or the more substituted side. You'll notice this has an R group and this one just has a hydrogen. So this is going to be the more substituted, this is going to be the less substituted. So what's going to happen is the halogen is going to be attracted to the more substituted carbon because it has a partial positive charge. This one has no partial positive charge, it's going to bind the hydrogen. And that's what we have here. So same thing, we got the same result, except we have our halogen bonded, there. And this one. So same thing. Now, for the excess HX mechanism, you just do the first mechanism twice. Why? Well, so this is just one equivalent. We end with an alkene. By the way, there's a hydrogen here. I just want to draw it in because I just want to show you the mechanism, but there's a hydrogen here if you're confused. That's why I said it's similar to this. Same thing. I didn't draw it in. Now, we use one equivalent here. So what happens if you use excess or multiple equivalents? Well, think about this. We have our alkene now, and we add more, for example, HBr, HCl, or HI. Well, then it's going to turn into an alkane, and we're going to add another halogen. This is exactly like the video I made on hydrohalogenation alkenes. It's the same thing. So if you just do, HX, the mechanism right here is exactly the hydrohalogenation of alkenes. We're just shortening it by saying excess. Excess. HX. It's the same thing. Instead of just saying, one equivalent of HBr and then 2 HBr, we're just saying excess. It's a shortcut. That's why. Practice problems. Tell me the following products for the following hydrohalogenation reactions. Okay, so we have an alkyne and we have excess HCl. 2 halogens. So since we have excess, we're going to have 2 halogens bond to our molecule, sacrificing the alkyne, and turning into an alkane. The halogens bond to the more substituted carbon. So this is more substituted than this because this has no branches, this has one branch. The halogens are going to bond here. And we're going to get an alkane. Like this. Now, gotta be careful. Where's this coming from? Counter carbons. Let's just say that this is carbon 1, this is 2, this is 3, this is 4. This is 1, this is 2, this is 3, this is 4. 4 is coming from here. That's why. We just straighten it out a little bit. That's why. B. Same thing. HBr, excess. Bromine's going to bind to the more substituted carbon. This is the more substituted. So bromine, and we sacrifice the alkyne and change it to an alkane. And we get this. It's pretty fast, right? Not too bad. Okay, what about this one? All right, we have excess sodium amide and liquid ammonia in water and excess HBr. What do? Well, if you skipped my last video, I talked about this. What this does is create an alkyne. This does 2 elimination reactions. So what we're going to do is we're going to create an alkyne, which is good. Then we can do our addition reaction of excess HBr. Okay, since we're doing 2 elimination reactions, we have to look at what the alpha and beta carbons are. Because the beta carbons is where the hydrogens come from, where we sacrifice. This is the alpha carbon, this is the beta carbon, this is the beta carbon. This beta carbon has no hydrogens to sacrifice, so that means we must sacrifice from this carbon. Okay, now remember the alkyne forms between the alpha and beta carbon. So we're going to get our alkyne here. by sacrificing these. And, well, these are going to let go. These are going to leave. And we're going to sacrifice our hydrogens. Okay, once we get our alkynes here, we can now do our addition reaction, adding our bromine to the more substituted carbon, and this is more substituted than this because there's absolutely nothing here, and then there's one bond here. So that's our answer. Hopefully that makes sense. All right, synthesis. Tell me the reagents needed to synthesize the product. I made a video on two-step synthesis not too long ago, and it was a very helpful video, and I see that you guys liked it a lot because it's doing really well. I told you there are two key techniques. When you want to move atoms from one position to another, you always do an elimination reaction first, and then you follow with the addition reaction. That's what we're doing here. You also need to do hopscotch. You must see how many carbons the molecules or atoms are moving. Let's take a look here. We're starting at 1, 2, 3, 4, 5. Okay, the halogens are carbon 5. Compare here. 1, 2, 3, 4. Okay, we are now, the product, I should say, has the halogens at carbon 4. We started at 5, we're ending at 4. We have moved one carbon over. That must mean we're going to do our cheat code where we do the elimination reaction first and then we do the addition one time. For example, if we were moving 2 carbons, for example, we would do that cheat code twice. We would do an elimination reaction, then we would do an addition reaction, then we do an elimination reaction, and we do an addition reaction. Okay, we're only going to do it once though, because we're hopping one carbon over. Well, what's the addition reaction to get an alkyne? Because in order to add 2 halogens, we need an alkyne. And that the elimination reaction we did is literally this. Sodium amide and liquid ammonia and water. Okay, we did that. So that's our elimination reaction. Now we need to add our halogens. Well, we have chlorines. We're just going to use excess HCl. Ta-da! And that's it. If you found this video helpful, please like and subscribe. Until next time, later.